Seeing the aurora like this is an amazing experience, and it is quite easy to capture it. In this video I will break down where you can see the aurora, how you can find out when it's visible, and also how to photograph it with your phone or camera. You can jump to single parts by clicking the chapters in the description. Also a small disclaimer, I am not an expert and will probably get some of the physics wrong, so please don't roast me too hard for that. So now, let's get on with the video. First of all, where can you see the aurora? Most people know that in Alaska, northern Canada, Scandinavia and Iceland you can see the aurora. But it also in some cases is visible in the Alps or at the Mediterranean Sea, and also in the south. It's dependent on the strength of the aurora. The further north you are, the more likely you are to see it. And the most obvious thing, it needs to be dark outside. Therefore, it is way more likely to see it in the winter than in summer. Then we also need to be clear on what we mean when we say see the aurora. There's a difference between being able to see it with your bare eyes and the aurora being visible with camera equipment. I will try to grade the videos and photos in a way that I show you what the camera saw and what was visible with the naked eye. Most of the photos are taken around Kiel at the Baltic Sea. We actually can see the aurora quite often here as a glow on the horizon. That is a lot different to what people are used to from Instagram and the pictures from Iceland. It is quite faint and not straight overhead. If there is a strong aurora, however, it can also be visible straight above in northern Germany. But what is the aurora exactly? Now it gets a bit scientific. Magnetospheres and geomagnetic storms. Many planets, including Earth, are surrounded by a large magnetic shield called a magnetosphere. On Earth, this shield stems from the churning molten metal core inside the planet and extends far out into space. Our magnetosphere protects us from harmful charged particles in the space environment. As these particles collide with the magnetosphere, they can transfer energy to the magnetosphere itself. However, if certain regions become overloaded, a geomagnetic storm can erupt, just as rain clouds swell with water droplets preceding a thunderstorm. During a geomagnetic storm, much of the accumulated energy in the magnetosphere flows down along Earth's magnetic field lines, precipitating into the atmosphere like a summer downpour on the prairie. This type of particle precipitation injects millions of amps into the atmosphere, leading to impressive auroral displays in places far from Earth's poles. Coronal mass ejections. Occasionally, magnetic storms on the Sun eject large amounts of solar material into the solar atmosphere. These huge flying blobs of sun stuff are called coronal mass ejections, or CMEs. If directed at Earth, fast-moving CMEs can reach our planet in as little as 15 hours. The Sun is approximately 93 million miles away from Earth. A CME arriving here in 15 hours means that it's traveling around 6.2 million miles per hour, or about 0.9% of the speed of light. As they billow away from the Sun, fast CMEs can overtake slower-moving, charged particles ahead of them in the solar wind. These particles are accelerated as they are swept into the careening solar ejector, increasing the risk and intensity of a radiation storm when they reach Earth. Under certain conditions, CMEs can supercharge the magnetosphere as they blow past, creating powerful geomagnetic storms in response. Magnetic reconnection. As we've seen, the solar wind emanating from the Sun flows around Earth's magnetosphere like a river rushing around a rock. This onrush of charged particles stretches Earth's magnetosphere away from the Sun, creating a long wake known as the magnetotail. The magnetic shields of the Sun and Earth are polarized, like refrigerators and the magnets that adhere to them. The polarity of Earth's magnetic shield is mostly stable, but the Sun's can vary due to its more dynamic nature. Sometimes, the magnetic polarity of the solar wind is opposite that of Earth's magnetosphere. When the solar wind buffets the magnetosphere under these conditions, the field lines of the Sun and Earth snap together, similar to when an everyday magnet connects to a fridge. This is called magnetic reconnection. The continuously blowing solar wind then pushes these newly connected Sun-Earth field lines, wrapping them around the magnetosphere and stretching them out toward the magnetotail. Eventually, these field lines stretch to their limit and snap like a rubber band. This severs the direct Sun-Earth magnetic connection, releasing energy back along the field lines and reinstating the original magnetic configuration in the process. Depending on the strength and other factors, we see different colors in the aurora. In height of around 240 kilometers and higher, we see red aurora. Red aurora is only visible under intense solar activity as there is a low concentration of oxygen in that height. Up to 240 kilometers height, we see green aurora as there is a higher concentration of oxygen. Above 96 kilometers, we can see purple aurora when there is intense solar activity, but this time it is ionized nitrogen that we see. Below the purple aurora, there is a chance of blue aurora that is also only visible with intense solar activity. Where do these values come from? Measuring the interplanetary magnetic field. The real-time solar wind and interplanetary magnetic field data that you can find on this website come from the Deep Space Climate Observatory, or short DISCOVER, satellite, which is stationed in an orbit around the Sun-Earth Lagrange point 1. This is a point in space which is always located between the Sun and Earth, where the gravity of the Sun and Earth have an equal pull on satellites, meaning they can remain in a stable orbit around this point. This point is ideal for solar missions like DISCOVER, as this gives DISCOVER the opportunity to measure the parameters of the solar wind and the interplanetary magnetic field before it arrives at Earth. This gives us a 15 to 60 minute warning time, depending on the solar wind speeds, as to what kind of solar wind structures are on the way to Earth. Solar cycles and activity. The solar cycle, also known as the solar magnetic activity cycle, sunspot cycle, or Schwabe cycle, is a periodic 11-year change in the Sun's activity measured in terms of variations in the number of observed sunspots on the Sun's surface. Over the period of a solar cycle, levels of solar radiation and ejection of solar material, the number and size of sunspots, solar flares and coronal loops all exhibit a synchronized fluctuation from a period of minimum activity to a period of maximum activity back to a period of minimum activity. Solar cycle 25 began in December 2019. Several predictions have been made for solar cycle 25 based on different methods ranging from very weak to strong magnitude. A physics-based prediction relying on the data-driven solar dynamo and solar surface flux transport models seems to have predicted the strength of the solar polar field at the current minima correctly and forecasts the weak but not insignificant solar cycle 25 similar to or slightly stronger than cycle 24. Notably, they rule out the possibility of the Sun falling into a Maunder minimum-like or an inactive state over the next decade. They expect solar maximum to occur between 2023 and 2026 with a sunspot range of 95 to 130. Now that we have a basic idea of what the aurora is, how can we determine when and where it will be visible? There are different websites and apps. Spaceweatherlive.com has a good website and also apps for your phone, where you also get notifications. There are many more apps, but in the end, they all use data made available by different institutions. I will focus on this app to explain to you a few different things. KP Index. The KP Index is a standardized global measure of geomagnetic activity ranging from 0 to 9. That indicates the strength of solar particle radiation's effect on Earth's magnetic field. High numbers, especially 5 and above, indicate a stronger geomagnetic storm and can lead to visible aurora displays at lower latitudes and potential disruption to electronic systems like satellites, power grids, and GPS. Solar wind speeds. Solar wind speeds typically range from 300 to 800 km per second, with a fast wind averaging around 800 km per second, originating from coronal holes, and a slow wind averaging 300 to 400 km per second from equatorial regions. Speeds can dramatically increase during coronal mass ejections, sometimes exceeding 1000 km per second. Density. Solar wind density, a measure of the number of charged particles, protons, and electrons per cubic centimeter, significantly impacts the aurora's intensity. Higher density, especially above 8 particles per cubic centimeter, generally leads to more active and brighter auroras, while lower densities can result in less promising conditions. Interplanetary magnet field. The BT value of the interplanetary magnetic field indicates the total strength of the interplanetary magnetic field. It is a combined measure of the magnetic field strength in the north-south, east-west, and towards Sun versus away from Sun directions. The higher this value, the better it is for enhanced geomagnetic conditions. We speak of a moderately strong total interplanetary magnetic field when the BT exceeds 10 NT. Strong values start at 20 NT, and we speak of a very strong total interplanetary magnetic field when values exceed 30 NT. The units are nanotesla. BZ. The north-south direction of the interplanetary magnetic field is the most important ingredient for auroral activity. When the north-south direction of the interplanetary magnetic field is oriented southward, it will connect with Earth's magnetosphere, which points northward. Think of the ordinary bar magnets that you have at home. Two opposite poles attract each other. A strong southward BZ can create havoc with Earth's magnetic field, disrupting the magnetosphere and allowing particles to rain down into our atmosphere along Earth's magnetic field lines. When these particles collide with the oxygen and nitrogen atoms that make up our atmosphere, it causes them to glow and emit light, which we see as aurora. For a geomagnetic storm to develop, it is vital that the direction of the interplanetary magnetic field turns southward. Continued values of -10 NT and lower are good indicators that a geomagnetic storm could develop, but the lower this value goes, the better it is for auroral activity. Only during extreme events with high solar wind speeds it is possible for a geomagnetic storm to develop with the northward BZ. In the graphics you can see that currently there is not much going on. The good thing is, as these values come from satellites, you can see the values that will reach the Earth somewhere between 20 to 60 minutes after it shows up. For me, that is usually good enough to decide whether to go out or not. I'm situated around the Kiel area of the Baltic Sea, and these are the values I tend to go out for. Photographic aurora KP index of 5 or higher. BZ at -8 to -10, and for visible aurora without gear, I usually go for a KP index of 6 or 7 and the BZ at -20 or lower. You will need to find a good spot that is dark without light pollution and no light pollution towards the north. There are also different websites that show you good areas, and obviously the weather needs to be good enough. Not only straight above but also to the north, as for example here we often see the aurora on the horizon that is somewhere over southern Norway. Okay, now that is a lot of information. At what values can I see the aurora in different parts of the world? The answer is everything but easy. As always, it depends. I will give you a few examples and values I would go out for. But keep in mind that you will also need to check for clouds and light pollution. Photographing the aurora with your phone. The good thing is you will be able to take very nice photos with a moderately modern phone. You just need to keep a few things in mind. First of all, if you can, use a tripod or any other form of stabilization, as we will need to do a longer exposure. If you have very steady hands, the iPhone for example guides you a bit. That works but won't give the best results. You can also try to lean it against something as a makeshift tripod. Then make sure you are photographing on a wide lens, and please do not zoom in or out in between the lenses. You will lose a lot of quality. The phones will have some sort of night mode. On the iPhone you can also change the settings for the night mode, where you can choose between different exposures. Depending on how bright the aurora is, you can try different exposure times. You can also try different compositions. Try photographing horizontal or vertical. Play with different things in the foreground. With more or less sky in the picture, experiment a bit. Photographing the aurora with your camera. You can take amazing pictures of the aurora with basically any camera, as long as it has a manual mode where you can set aperture, shutter and ISO. You ideally want to use a low aperture wide angle lens like 16 to 35 f2.8, but it also works with most standard lenses like 18 to 55. And also you will need a tripod. Okay, let's get into the settings. The camera will have a very hard time to determine the white balance and is often too yellow. So set it manually to around 4000. Open the aperture up as much as possible and set the focus to manual. Try and focus on a star in the sky. That way you will ensure sharp photos. Now, the aurora is quite active and moves around. Sometimes it also looks like it's almost breathing. Therefore, you don't want your shutter too slow. Try starting at around 1 to 2 seconds. Now, to control the exposure, we will vary the ISO. meaning you start at an ISO level and adjust it if it's too bright or too dark. Usually I start at around 30,200. Now, to get the best photos, I usually use the interval mode on my camera, set to an interval of around 4 seconds. Then I take at least 300 pictures and choose the best one or make a time-lapse out of it. I hope you enjoyed the video. If you have any questions, put them in the comments and I will try to answer them. See you next time.